and the data structure used in deadlock avoidance, Banker's algorithm, will also be useful. So, but before that, I would like to tell you the concept of deadlock detection. Actually, deadlock detection allows the system to enter into the deadlock state and after that it applies a detection algorithm, and once the deadlock has been detected, we have to recover the system from the deadlock. Okay, there are two parts of this approach. One is deadlock detection and another is deadlock recovery. So first we will discuss the deadlock detection and then we'll move towards the deadlock recovery. So there are two possibilities, that there is a single instance of each resource type. If there is single instance of each resource type, the strategy used for deadlock detection is wait for graph. Okay, actually wait for graph can be created from resource allocation graph. Deadlock detection, when the single instance of each resource type is available, we can generate a wait for graph from the resource allocation graph, and periodically we invoke an algorithm which search for a cycle, and if there is a cycle in the graph, we say that the system is in deadlock state, and if there is no cycle in the graph, the system is not in a deadlock state. But this graph detection algorithm, cycle detection algorithm, the graph requires order of n square operations. So let me tell you how we can generate wait for graph from resource allocation graph. As I told you in the earlier lecture, these circles are processes and these rectangles are resources. So we have in the system 5 processes, P1, P2, P3, P4 and P5, and we have 5 type of resources, R1, R2, R3, R4 and R5. We have single instance of each resource type, and this is a request stage. P1 is requesting for one instance of R1, whereas one instance of R1 has been allocated to P2. This is an this is a request edge and this is an assignment edge. Okay, so P1 is requesting for resource type R1 and R1 has been allocated to resource type P2. Similarly, P2 is requesting for resource type R3, which has been allocated to P5. So this resource allocation graph basically shows the system state at present time. Okay, now from this resource allocation graph, we can construct a wait for graph. For wait for graph, there will be only processes, there will be no resources. Okay, and how these edges of this graph will be decided, I will just tell you. Because if there is an edge from P1 to R1 and there is an edge from R1 to P2, there will be an edge from P1 to P2. There is one edge this P1 to R1, there is one edge R1 to P2, so there will be one edge P1 to P2. Similarly, suppose see this, there is an edge from P2 to R4 and R4 to P3, so there will be an edge from P2 to P3. This edge is like this. Now you say that, see this, that there is an edge from P2 to R5 and R5 to P4. So there will be an edge from P2 to P4. Okay. So by considering all such pairs, we can construct a wait for graph from resource allocation graph. So this is the resource, this is the any doubt? Any doubt till now? Okay, so basically this is the resource allocation graph, and from this I am able to construct this wait for graph. So now in order to check whether the system is in deadlock state or not, I need to just check whether there is a cycle in this wait for graph or not. So if I see the cycle P1 to P2, P2 to P3, this to this, then this to this, and then this to this, there is a cycle. the system is in deadlock state. So this is a simple approach. So this is a simple approach, and we can find whether the system is in deadlock state or not. But the problem with this approach is, first of all, it is applicable to system only when there is a single instance of each resource type. If there is multiple instances, this will not work. Multiple instances, this approach will not work. Okay, so for that purpose, what we have to do, second problem is this is resource intensive. Order of n square operations are required. So when we have multiple instances of each resource type, the approach is similar to the Banker's algorithm, and the data structure is also similar. So deadlock detection के लिए what we do, we take an array available. Just one second. This available is basically tells me how many resources are available in the system at any point of time. This allocation tells me what resources are allocated to each process and what type of resources. And this request basically tells me what is the current request status of each process. So we will take one example, and from that it will be clear how it can be done. So, and these data structures we have already discussed when we were discussing the Banker's algorithm. So I'm not going into the detail of that. So detection algorithm, work is a data structure, temporary data structure required in this approach. So work is equal to available. Whatever resources are available with the operating system are assigned to the work. After that, we make finish I is equal to false, and we try to find an index such that finish I is equal to false and request is less than work. Because unless the request, whatever a process is requesting, that much resources must be available with the operating system. Unless that is true, we cannot satisfy the request of that particular process. So in this case, if no such I exists, we will have to go to step 4. Otherwise, okay. Now, if we find such an I for which the request was less than the work, we assume that that request will be satisfied by the operating system, and whatever resources were previously allocated to that process will also be returned back to the operating system, and that process will be finished out of the system. So when we reach to the process step 4, there are two possibilities. Either finish I is false for all the processes. If this is the case, system is not in deadlock state, no deadlock. Sorry, if the system finish I is equal to false for a single, even for a single process, then the system is in deadlock state. And if deadlock is finish I is true for all the processes, the system is not in deadlock state. Deadlock, and if finish I is equal to true for all, system is not in deadlock. That means we are able to satisfy no deadlock. So in this way, this works, but we will take one example, and from that I will like to tell you how this is working. So the algorithm requires order of m into n square operations. So this is also a resource intensive approach, because if the number of processes are more and the number of resources are more, then it will take a lot of time. Now you see, we take one example, and from that example we will try to. Any doubts till now? No? Okay. So there are 5 processes: P0, P1, P2, P3, P4. These are the resources allocated. There are 3 resource types, A, B, and C. And this is the current allocation. Process P0 has been allocated 0 instance of A, 1 instance of B, and 0 instance of C. Process P2 has been allocated 2 instance of A, 0 instance of B, and 0 instance of C, and so on. This is the current request status of P0, P1, P2, P3, and P4. P0 is not requesting anything. P1 is requesting 202. P2 is requesting 000. P3 is requesting 100. P4 is requesting 002. And this is the available status. These are the resources available with the operating system. Now we have to find whether the system is in deadlock state or not. For that purpose, we have to apply the deadlock detection algorithm, and for that purpose we have to, my work is equal to this. This is my work. Because if I am able to find some safe sequence, I will be able to say that the system is not in deadlock state. Okay, finish. I make all this false. This is false. This is false. Because now I have to find a process whose request can be satisfied from this work. So P0 is one such process who is not demanding anything. So I will assume that the P0 will finish its work and will revert back the resources which are allocated to this. So here resources 0, 1, 0 hai, these will be added in the work. So my work will now be 0, 1, 0, and this will be now true. P0 is now true. Okay. So now another thing, we can satisfy the request of this also, because the now available is this, work is this, and the resource request of P2 is 0, 0, 0. So mera P0 true ho gaya. Now I will assume that because I am able to satisfy the demand of P2, whatever resources have been allocated to P2 will also be returned, and this will be added in the work. So this 303 will be added in the work, and this will become now 3, 1, and 3. Now I can satisfy the demand of P1 because it is 202 and the available with me is 313. So I can satisfy the demand of P2 also. So ये P1 ये मेरा P2 true हो गया था. Now I will satisfy the demand of P2. So this will be satisfied, and this 200 will also be added into it. Now 5, 1, and 3. This is the work available. This now P1 also true. Now I can satisfy the demand of P3. And after that, I will be able to satisfy the demand of P4. So there is a safe sequence exists, that is P0, P2, P3, P1, and P4. And I will be able to say that the system is not in the deadlock state. Okay. Shall I move ahead? This example is clear. Okay. So now suppose P2 requests an additional instance of type C. So in that case, the request will now become like this: 000, 201, 001, 100, 002. So now I have to check whether the system is in deadlock state. I can repeat the similar process, and I will be able to find that now the system is not sufficient to fulfill the request, and there is no safe sequence which exists. So the system is now in the deadlock state. So I give you 2 examples, and one in which the system is in deadlock state, and second in which the system is not in deadlock state. Now, there are two other things which we have to consider if we are using the deadlock detection and recovery approach. First thing is that when the deadlock detection algorithm should be invoked and how frequently this deadlock detection algorithm should be applied, because every time I apply a deadlock detection algorithm, some cost will incur. It will incur some cost, because whether I apply the wait for graph approach in single instance type or I use the deadlock detection algorithm based upon Banker's algorithm, that will also incur some cost. And if I apply it too frequently, that will be wastage. And most of the time I will say that there is no deadlock and I will wasting my time. But if I delay it very far, then the system will remain in deadlock and we will not be able to recover for a long period of time because we have not detected, we have not applied the deadlock detection algorithm. So it depends upon the frequency of deadlock in the system that decides how often I should apply the deadlock detection algorithm. Now, once the deadlock has been detected, that we have to recover from the deadlock. There are two possibilities. One is process termination and second is resource preemption. Process termination, suppose we have found that there are certain 5-6 processes are in deadlock state and we have to remove this deadlock. So one possibility is that we abort one process, we terminate one process and the cycle will be broken, and then we will be able to say that the deadlock we will assume that that if we terminate this process, the cycle will be broken and the system will remove from the deadlock state. But we have several processes which are in the deadlock state and we have to select which one to select so that the system is not affected. So there are several criteria based upon which we can select which processes to which process should be aborted. One is the priority of the process, because if I abort a high priority process, that will create problem in my system. Okay. And second thing is how long a process has computed and how much time it more requires. Because if a process was about to complete and it had completed its 95% of tasks and I abort that process, I terminate that process, that will be a huge loss for the system and that process has to be restarted from the beginning. What resources the process has used, what are the resources which are required by this process, which have been used by this process, this is important. Which processes it requires, and will it be sufficient to abort that process? Or suppose there is a deadlock like this, P0, P1, P2 and P3. And if we say that this is the wait for graph, suppose this is the wait for graph, if I abort this process, system will remain the, okay, just one second. This is the wait for graph for a particular system at a particular point of time. If I abort this process, because there is cycle like this and this, there is cycle like this, and if I decided to abort this, will the deadlock will be removed from the system? No, because still there is a deadlock between P1 and P3. So it is not a wise decision to remove this process. Instead, if I remove this process, if I remove this process, this will remove this cycle and this cycle also. So this should be a better choice. P1 should be better choice to be aborted or terminated. So second thing, I have to select whether it is an interactive process or batch process. So based upon this, I can decide based upon these criteria. We can abort all deadlock processes, but that is very bad approach. Abort one process at a time until the deadlock cycle is eliminated. Okay, so these things we can take care. Another approach is resource preemption. Instead of aborting or terminating a process, we operating system tries to snatch the resources from the processes. Those who are involved in the deadlock, operating system sees because of what kind of resources the deadlock has happened, and instead of aborting the entire process, it snatches some resources from the processes, and based upon that it tries to remove the deadlock. But in this case there are basically two things. One thing, we have to roll back, and second thing, there is a possibility of starvation. If suppose there is a process P1 and P2 and P3, which are in the deadlock state, this is having a resource type R1, and the operating system snatch the and this is also requesting for R1 P1, and this is held by P3. Suppose operating system snatches the resource R1 from it and gave it to this one. So this process P3 has to be rolled back to a certain position, so that because this P3 was working on this resource R1 and it must have done some work. That work is not completed yet. That work will be wasted, and this process P3 has to be rolled back to a certain position. From there it can restart. Okay. Then second thing is the possibility of starvation, because if every time I select a particular process and operating system keep on snatching the resources whenever its turn comes, and the operating system continue to snatch the resources from the same process, this process may starve. It will not be able to make significant progress, and ultimately this will take a longer time, or ultimately the system performance will degrade. All these approaches we have discussed. We discussed prevention, deadlock prevention. We discussed deadlock avoidance. We discussed deadlock detection and recovery. So no approach is best, and for several separate type of resources, separate approach is required. For example, if I have some shareable resources, I can deny mutual exclusion. I can allow them to be used by more than one processes at one point of time, and I can use prevention, deadlock prevention, by denying the mutual exclusion thing, because I told you that in order to deadlock happen, 4 necessary conditions are required simultaneously. One of them is mutual exclusion. So if we are not able to, if mutual exclusion will not happen, the deadlock will not happen. But unfortunately,
Excuse me, sir.
Yes, please.
Sir, what is the meaning of rollback?
Okay, I tell you. Suppose there is a process P1. Okay, it is working on a suppose disk database. Okay. This P1 is working on this database on some transaction. And this transaction has certain parts. मान लिया इस पे एक काम कर रहा था, 5-6 स्टेप है इस ट्रांजेक्शन के. These 3 steps was completed when the operating system sees that this has to be snatched. Okay, now this database has to be snatched and has to be given to some other process. तो जितना काम इसने ये किया है, ये भी because the transaction आपको पता होगा, DBMS में पढ़ रहे होगे कि या पढ़ चुके होगे कि ट्रांजेक्शन जो है या तो पूरा का पूरा कंप्लीट होगा या पूरा का पूरा अबॉर्ट होगा. ओके, तो ये जितना काम इसने किया था, ये 3 स्टेप जो ट्रांजेक्शन के कर लिए थे, ये अंडू करने पड़ेंगे. तो इसको हम बोलते हैं रोल बैक. ठीक है, तो जितना काम इसने ये ट्रांजेक्शन के 3 स्टेप्स इसने कर लिए थे, 3 स्टेप इसके बाकी थे. अब ये डेडलॉक में फंस गया क्योंकि इसको कोई दूसरा रिसोर्स चाहिए था, जिसकी वजह से ये काम नहीं कर पा रहा था. Now the operating system decided that we have to remove the deadlock by resource preemption, and P1 was selected as victim, and this database has to be snatched from this process, and it has worked these 3 steps. Now this process, when this database will be snatched, ये प्रोसेस को हमें रोल बैक कराना पड़ेगा, जितना काम इसने ये कर लिया उसको हमें वापस करना पड़ेगा, अंडू, ठीक है। और जब ये प्रोसेस को दोबारा डेटाबेस मिलेगा तो ये यहां से शुरू करेगा जहां से ये 3 स्टेप कर चुका था, उनको दोबारा इसको करना पड़ेगा। आया समझ में आया भाई?
Yes, sir. Thank you.
So second possibility is if resources are numbered, तो हमने जो सीक्वेंसिंग की थी उसकी हेल्प से हम सर्कुलर क्यू को डिनाई कर सकते हैं। डेडलॉक तब बनता है जब P1 P2 की वेट कर रहा हो, P2 P3 की वेट कर रहा हो, ये ऐसे करके Pn की वेट कर रहा हो और Pn फिर P1 की वेट कर रहा हो। तो हमने बताया था कि अगर हम रिसोर्सेज को नंबर कर सकें, इफ वी आर एबल टू नंबर रिसोर्सेज इन ए लॉजिकल सीक्वेंस, और एक प्रोसेस जिसके पास छोटा रिसोर्स है वो बड़े रिसोर्स को मांग सकता है, बड़े रिसोर्स वाला छोटे रिसोर्स को नहीं मांग सकता, तो वो अगर हम डिनाई कर सके तो हमारा डेडलॉक नहीं होगा और हम सर्कुलर क्यू को डिनाई करके प्रिवेंशन कर सकते हैं। लेकिन वो दिस नंबरिंग इज क्वाइट टिपिकल एंड इट इज नॉट पॉसिबल इन ऑल टाइप ऑफ रिसोर्सेज, but there are certain type of resources in which this numbering is possible, okay, and if we are able to number the resources in logical sequence and we can deny circular queue, we can prevent the deadlock. Banker's algorithm is very important and frequently used. If we are able to tell the operating system what is our maximum demand, each process in the beginning is able to tell that this is my maximum demand, we can apply Banker's algorithm because this is quite general. It can be applied to all kind of processes. Multiple instances are allowed, although it is resource intensive and we have to apply it at every request, but this is quite general and quite useful. There is another thing, if deadlock is not so frequent, we allow the deadlock detection and recovery approach. If suppose the deadlock happens in every 2 hours, okay, so Banker's algorithm takes my 10% of the time, suppose. So it is not wise that for every request I apply the Banker's algorithm, at which is consuming my 10% time. If my deadlock is happening on an average 2 hours per deadlock, what I can do, I can apply the deadlock algorithm every 1 hour, okay, deadlock detection algorithm, and the deadlock is there, I can remove the deadlock by the process termination or resource preemption, okay. So this is one possibility. One very important, not very important, but very interesting approach is ostrich approach, okay. What we can do, if deadlock occurs once a year, we can allow the deadlock to happen and we do just nothing. What will happen in that case, after a certain period of time, all the processes will be in the deadlock state and we will shut down the system and we will restart the system. But this approach can be used only when the deadlock is very infrequent and only once a year or 6 months, twice a year this happens, then this approach can be applied. So this is the combined approach for the deadlock, and that's all for the deadlock. Now we will move to the next topic, which is disk management. Okay, mass storage structure are important because my RAM is volatile and my data and instruction, when I will switch off the computer, my data and instruction will be gone and I have to store it somewhere, okay, so that it can be used later on. Although the CPU cannot directly access the mass storage structure, but my data is permanently stored there. So this is important. So the most important disk structure, mass storage structure is hard disk. Okay, so this is basically the typical structure of a hard disk. And if you see, there are plastic plates coated with the magnetic material, and the 0 and 1 is stored in the, you can say, if clockwise and anti-clockwise. If magnetization is clockwise, it is 1. If it is anti-clockwise, it is 0. We store the bits in this form, and these are the heads. And you see, both the sides of the platter is coated with the magnetic material. There is a magnetic coating. So basically, and you see there is a spindle. First I am talking about the physical thing, then we will come to the logical things. This spindle, there is a motor which can rotate this spindle, and the location of this platter will change accordingly. Okay, now I talk about, there are multiple heads. Okay, and there are multiple tracks on each platter, and on in each track there is a sector. This is sector, this thing. This is the sector, and this sector is the basic unit of transmission. This can be, this is a block, basically we call it block also, and typical size of this block is 500 bytes, 512. It can be a multiple of 1024 bytes is also possible, but typical size is 512 bytes. And this is the basic unit of data transmission. Whenever data transmission, I want to read some data from a hard disk, the entire block will be read, basic unit, right? So whenever I want to transfer some data from the hard disk, I am talking about the transferring of one or more blocks. Okay, so now the question arises, how we can access. First of all, addressing is important, because I need to tell which block I need to transfer. And second thing is, I need to do the what physical operations need to be done. So I tell you, three things are required: cylinder, head, and sector. Okay, so track T, you see all track T's on all the plates make this cylinder C. Okay, this is one cylinder, this is one cylinder, this track, this is one track, this is another track, this is another track. So all these tracks are part of this particular cylinder. This is one cylinder. Okay, so I need to know which cylinder I am talking about. After that, suppose I want to talk about this sector. I need to know which cylinder I am talking about. I am talking about this cylinder. Then I have to tell which head I am talking about. I am talking about this head, right? So then this is decided that this is the part where I am looking for. Then I have to tell which sector. So I am talking about this sector. So in this way, if I know the cylinder number, head number, and sector number, I will be able to identify the particular sector. So the addressing in a hard disk is done based upon cylinder, head, and sector. Okay. Now, once the operating system will provide me this information when my user says that I need a block or a file, operating system first see where this file is stored, in which cylinder, which head, and which sector this file is stored. Now, once this is done, the device driver will generate the necessary commands. What we need to do, suppose this is the sector I want to read. Okay. So first of all, this read write head has to be positioned at this cylinder. This read write head may be here. This read write head may be here. There is a horizontal movement for this read write head, right? This read write head can make horizontal movement. So first of all, this read write head has to be placed here. Now this read write head is on that right cylinder. Now this spindle will be rotated so that this sector is under the read write head. अब मुझे इसको मूव करना पड़ेगा, ऐसे मूव हो रहा है, ऐसे मूव करके जब ये वाला सेक्टर यहाँ आ जाएगा, then the read write head can start reading the data from this particular sector. Is it clear to all of you?
Yes, sir.
Okay. So I move ahead now. Now the just one second. So magnetic disk rotates at 60 to 200 times per second. Transfer rate. Basically, this is important. How many bytes we can transfer per second from the hard disk to the memory, drive and memory. We are transferring data from hard disk to memory, and we are interested in the transfer rate, and sometimes this is also known as bandwidth. Okay. So there are basically two parts, or I should say three parts. First of all, there are two parts, I should say three parts. One is seek time. Seek time जो head जो है वो move करता है particular cylinder पे, ठीक है? Your head is make horizontal movement to reach to the particular cylinder, and that is known as seek time. Second is rotation latency. Once head is placed, now I have to rotate the spindle so that the particular sector is under the read write head. Okay, and third is basically the transfer. Once the head is just above the particular sector which we are willing to transfer, then the actual transfer will start. So basically the total time for transferring a data requires three things: seek time, rotational latency, and the transfer time. So these three things together decides how much time will be required to transfer a file from the hard disk to memory. Sometimes the disk head makes a physical contact with the surface, and in that case the head may crash. This is just, ये थोड़ा सा ऊपर चलता है, जो head है मेरा, this does not touch the magnetic surface, but it remains just above this, and it is able to sense whether the magnetization is in the clockwise direction or in anti-clockwise direction. Okay, there are various type of disks: EIDE, ATA, SATA, SCSI, now SSD. But SSD is basically a separate technology, which is these all disks are magnetic disks and using the magnetic material. But the SSD is a separate thing. We will discuss sometime later. Okay, now there are requests for there are several processes which are making requests in a multi-programming environment. There are various processes which are continuously making requests for disk access. Okay, and in that case, what we have to do as an operating system, we have to satisfy the request of these processes, and we have to satisfy the request in such a manner so that the throughput is good. We are able to satisfy the request times. We will be able to provide good uh, response time to all the processes, and in that case the disk scheduling algorithms plays an important role. Suppose there are n number of processes, say P1, P2, P3, and these are requesting different sectors. I told you we can address a sector in two manners basically. One is hierarchical, cylinder, head, and sector. And second addressing is LBA, logical block addressing. Okay. In logical block addressing, what we assume that we have suppose 5,000 sectors, 0 to 4999. We consider the sectors as a linear array of 0 to 499, and each sector will have a unique number in this. Okay, but ultimately physically the addressing is like this. This is a logical addressing, logical block address. But the operating system has to convert this logical block address into cylinder head and sector. But that is the responsibility of the operating system. Okay. Now what we are assuming that there are multiple requests, multi-programming environment hai mera. And there are multiple requests for a disk access which are continuously coming, and the operating system has to satisfy these requests in a logical and efficient manner. So for that purpose, there are various algorithms, disk scheduling algorithm. So we want to reduce the access time, seek time, rotational latency we want to reduce, and we want to increase the bandwidth, disk bandwidth. This is our objective, besides providing good response time. So there are various disk scheduling algorithms which we are going to discuss in a short while, but the objective is minimizing seek time and rotational latency and maximizing disk bandwidth. So this is our objective. So for that purpose, we take one example. We assume that the current head is just this is the current position of the head. This is the request by several processes. One process is requesting for sector number 98, another is requesting for sector number 183, another is requesting for sector number 37, and so on. Okay. So first algorithm is FCFS. This is basically we are talking about cylinder number, not sector number, because reaching to a cylinder is important. Because एक बार एक cylinder पे पहुंच गए तो फिर उसके बाद तो फिर time कम लगेगा. This is FCFS. FCFS scheme में what we do, which request comes first? We are at 53. We are currently at here. The first request is 98. So the operating system will move from 53 to 98. Next request is 183. So it will move from 98 to 183. Next is 37. So it will come to here. Then 37 to 122, 122 to 14, 14 to 124, and 124 to 65 and then to 67. So no other consideration is there. Assuming that we have to be fair, who has requested first must be served first. So FCFS is basically uses a first come first serve approach. Now we have to calculate the total head movement. How many cylinders the head has to move? 53 to 98. The head movement is 45. 45 to 183. 183 minus 45. This is basically 138. 138. Then 138 to 183 to 37. This will be 146. Then 37 to 122. This will be 37 to 122, 85. Then 122, 14. That is 108. Then 14 to 124. That is 1110. Then 124 to 65. This is 59 and then 2. The total head movement to satisfy these requests is the sum of all these numbers, and that comes out to be 640. Okay, but can we reduce this? Because the seek time is directly proportional to the, and if I see the total seek time of this bunch of requests, that is directly proportional to the number of head movement made by the head to serve all these requests. So can I reduce this? So there are various other algorithms which are significantly able to reduce this thing. One is SSTF, shortest seek time first. It sees I have certain requests available to me. I have head location at a point. It sees which is the closest request, which will require shortest seek time, and it will satisfy that request first instead of serving the or request in a particular order. Okay, so if we see in this case, we are at 53, and this is the requests available to us. It will see which is the closest request to 53. Okay, and the closest request to 53 is 65, because the distance between. One more thing, the head movement is also important. Okay. Okay, sorry. So the distance between 53 and 65 is 12. Distance between 53 and 37 is 16. Though these are the two closest approach, but this is the best approach. So we move 53 to 65 by making a movement of 12. After 65, the closest is 67. Now it is 2. After 67, there are two possibilities. This is 137 and this is 98. Though this distance is basically 31 and this distance is 30. Okay, so we move to 37. ये हमने 30 approach use किया. After we move to 37, we move to 14, which is closest to it. Now the distance is 23. Now what is left? This is done. 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 Now 98, 122, 124, 183, and 199 left. Sorry, this is the last. This is not the request. So from 14, we will move to 98, making a head movement of 84. Then from 98 to 122, 24 head movement, and then the head movement of 2, and then the head movement of 59. So if you see, the total head movement is significantly reduced. 61, 85, then 169, 171, 203, 226, 226 and 12, 238. Instead of 640, we are able to make significant improvement on only 238 head movement. Okay. But the problem with this approach is this is not fair, first of all. And we can design better approach. We will further reduce our head movement. So let us see these algorithms. Next algorithm is scan. Scan में हम क्या करते हैं? The disk arm starts at one end of the disk and moves towards the other end, servicing all the requests until it gets to the other end of the disk, and then it reverses the head movement. This is also known as elevator algorithm. ये क्या करेगी? ये यहां से चलेगी यहां तक, एंड तक. सारी रिक्वेस्ट, whatever the requests are in the middle, these will be served, and then we will move in this direction, and whatever requests are there, these will be served. Elevator algorithm is like this because the lift, if we are in a high-rise building and we are using lift, so जो भी रास्ते में request, once it is moving in the upper direction, तो जो भी ऊपर जाने वाले रिक्वेस्ट हैं बीच में उन सबको सर्व करती हुई चलेगी, और उसके बाद में फिर ये मूवमेंट अपना रिवर्स करेगी और नीचे जाने वाली जो भी रिक्वेस्ट हैं उनको सर्व करती हुई चलती है लिफ्ट. तो उसी तरह से मेरा ये एल्गोरिथम है. That's why I call it elevator algorithm. So let us see how many head movements are required for the same example, and this shows 236 head movement. So let me see how it works. So there is a head movement also. I must know what is the current head movement. The current head movement is in this direction. So it will move from 53 to 0, and these are the two requests 37 and 14, which will be served in the middle. This will be served, this will be served, then it will move towards 0. तब ये 0 तक जाएगा. After that it will reverse its direction, and first it will satisfy 65, then 67, then 98, 122, 124, and 183. So this is basically the scan algorithm, and with the help of this, we are able to satisfy the requests in a particular order. Okay, not in the order of their occurrence, but order of their location. With the help of this, we are able to get little bit better results than the SSTF. Small improvement in this approach is C-scan. If you see, this movement is basically useless. This movement from 14 to 0. Why I am going to 0? Why cannot I reverse the direction from here to here? Because I know, the operating system knows that there is no request beyond 14, and 0 और 14 के बीच में कोई request अभी pending नहीं है, तो ये movement मैं बचा सकता हूँ. और C-scan में यही approach होती है. Circular scan is just a small modification in that, and instead of going to 0, in C-scan it will start reverse direction, and from 14 itself, which is the last request in this direction, and it will start, and it will be able to save these 14 head movement. So 236 minus 14, head movement here will be 222. Okay, this will further improve my bandwidth and the throughput. This is C-scan. Then there is another algorithm which is look. 1 minute, sorry. I am sorry, I just mixed two things. I am again repeating the C-scan. C-scan is basically a different approach. What it does, the head moves from one end to the disk to the other end. Okay, when it reaches the other end, then instead of serving the request, it automatically moves to the beginning of the disk. It returns to the beginning of the disk first, and then starts serving then it start returning. The logic behind this approach is रास्ते की जो रिक्वेस्ट है वो तो हम सर्व करते हुए आ रहे हैं। मैं आपको एग्जांपल से बताता हूं कैसे ये काम कर रहा है। दिस इज सी स्कैन। ओके, तो माय suppose the direction of the head was like this from there to there, then this is just similar to the scan. We move to this, then we move to this, then we move to this. After that, instead of serving these, अगर ये scan होता तो पहले 37 को करता, उसके बाद फिर 14 पे जाता, बट ऐसा नहीं है। यहाँ पे ये सबसे पहले यहाँ जब लास्ट में पहुंच गया तो it will move to the zero. First of all, it move to the zero, and then we'll start the direction in this direction again, and उसके बाद 14 को 14 को सर्व करेगा, फिर 37 को सर्व करेगा। इसके पीछे लॉजिक ये है कि ये जो रिक्वेस्ट है ये वाली, इस एरिया की रिक्वेस्ट तो मैं अभी सर्व करते हुए आ रहा हूँ, देयर इज वेरी लेस प्रोबेबिलिटी दैट यहाँ पे कोई रिक्वेस्ट बची होगी। तो इन सब रिक्वेस्ट को सर्व कर में टाइम वेस्ट करने की बजाय सबसे पहले मैं यहाँ पहुंच जाता हूँ, विच इज द अदर एंड ऑफ द दिस, और यहाँ पे कुछ रिक्वेस्ट पेंडिंग होगी, जल्दी से उनको मैं सर्व कर पाऊंगा। तो बेस्ड अपॉन दिस assumption, this C scan is used, and this is helpful in achieving the better response time. Although the head movement, I need not to consider this head movement because this is this can be done quickly without considering whether there is a request or not. यहाँ से यहाँ तो मैं एकदम पहुंच जाऊंगा बिना कुछ, क्योंकि मुझे किसी बीच की कोई रिक्वेस्ट नहीं देखनी है, तो यहाँ से यहाँ तक पहुंचने में मुझे टाइम नहीं लगेगा। So our next algorithm is look, which I am telling you just before that. Scan is similar. This is similar to scan. The only thing is that after moving from 57 to 37 and 37 to 14, it does not move to 0. Instead of moving to 0, it start moving in this direction. Okay, ये 14 का जो मूवमेंट है ये हमने बचा लिया। यहाँ पे जो हमारा 222 था उसमें से 14 का मूवमेंट हमने सेव कर लिया, तो नाउ वी रिक्वायर ओनली 208, and this is again a improvement over what we were trying to achieve. Okay, last algorithm, then I will wind up my class. Another is C loop. This is a version of C scan. जैसे स्कैन का वर्जन लुक था, स्कैन को इंप्रूव करके हमने लुक बनाया, और सी स्कैन को इंप्रूव करके हमने सी लुक बनाया। बस ये है कि arm only goes as far as the last request in each direction and then reverse the direction. Okay, so from the example it will be clear. Okay, you see from there to there, then there to there, here, 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 here. In C scan ये यहां तक जाता और फिर ये यहां तक जाता और फिर ये वापस शुरू करता अपनी डायरेक्शन। ठीक है, तो ये मूवमेंट अननेसेसरी है, ये मूवमेंट अननेसेसरी है। तो दीज टू मूवमेंट्स आर सेव्ड इन सी लुक, जस्ट it works just like look, but these two movements are saved. Instead of going to 199, it will reverse the direction from 183 and it will move to 14, 183 to 14 instead of moving to 0. These two movements are saved, and because of that we are able to reduce significantly our that thing. Okay, so that's all for today. Any doubts?
No, sir.
So these scheduling algorithms are very important for maintaining the performance. Okay, so but we cannot say which one is better because it depends upon situation, it depends upon workload, what kind of workload is available, Actually, these elevator algorithms are very useful when there is a heavy load on the disk. Okay, and shortest seek time give me good performance when the heavy load is not there, and I am able to give good response time and good bandwidth. But when the disk load is heavy, that elevator algorithm works well. क्योंकि जब हम एक डायरेक्शन में चल रहे हैं तो रिक्वेस्ट मुझे मिलती चली जाएंगी, उनको मैं सर्व करता हुआ चला जाऊंगा, फिर दूसरी डायरेक्शन में जब आ रहा हूं तब भी मुझे रिक्वेस्ट मिलती चली जाएंगी,